to one and all present here. Today, let's talk about the topic advanced digital signal processing. Uh, in this session, you will be looking into a brief outlook about the field of DSP engineering. Let's pitch in by understanding ourselves of what really DSP means, and then we look into a few comparison study uh, with respect to digital processing and analog processing. We'll also take up a case study and understand the basic fundamentals and the state of the art uh, behind DSP technology. We'll look into the evolution in the field and how the data processing demand has been fulfilled and various job opportunities and career path which one could, if interested in DSP engineering, could pursue in particular domain or stream and if one is interested in this domain. Let's begin with understanding what signals and system means. We'll be dealing with the terminology signals and systems in many places in this session. A signal is a function that conveys information to the user. Uh, it would if it is represented in terms of time or in terms of amplitude or in frequency or combination of these, then we can convey some information out of these parameters. And then a system is one entity that operates on these signals and interacts to perform a desired operations. Let's imagine a system being a black box. Then input signal are accepted into this black box. Either it is modified or synthesized to generate a set of output signals. I was talking about the system being a black box. So let's say if the input signal are inputted into the black box, then this set of operations in the black box would either modify or synthesize to generate a set of output signals. So it's one form of analysis. Or in other form of analysis is the system will accept the input signal, perform measurements or extract characteristics or information from these signals and give useful parameters to the users. For example, let's consider the speedometer case where the speed of the vehicle is measured using a system, or a voltmeter where the voltage will be pursued or conveyed to the user of the particular circuit of interest. Let's talk about DSP system in particular because that's the topic today. So DSP system is that system which operates on digital signals only. So digital signals, if we have to understand, it's a discrete time domain signal. Uh, let's say it is sampled or been uh, take of a discrete value in fixed interval of time, while will we consider a real world signal like audio or video or even image, all the real world signal are generally in continuous time domain, and a process of conversion has to be done before it is being uh, uh, inputted to a DSP system. That's called digitization. We'll understand that later. So giving a few examples on signals or real world signals and DSP systems, we'll talk about audio signals and its corresponding DSP systems like audio compressions algorithms or speech recognition algorithms. It is best examples when considered a music signal or a speech signal to be highlighted. Well, the conversation that we are having right now, the speech of my webinar is being converted using a microphone into a digital domain. Then it is processed on the PC using a DSP system on the host, then such that it is suitably modified to be transmitted on a physical channel that could reach you, and then it is converted back into an analog signal so that you could use it to listen to my speech. So this is the entire signal processing chain. So likewise, there is video signal and a particular DSP systems like pattern recognition or video compression, and also the radio signal, wherein the complete baseband processing in the advanced software defined radios are completely realized using quadrature modulation and demodulation techniques. And also the channel errors, like there is a lot of noise in, if there are a lot of noise in the physical channel, the channel coding and source coding will help to identify errors and detect or perform correction on the identified errors on the received data. So there are n number of applications, n number of audio real world signals which could be listed, and the list goes on. So in order to perform the DSP, we know that the real world signal has to be converted into a digital signal. So in order to do that, a basic principle has to be followed in order to perform processing on a DSP processor. So the first principle is called sampling. So it is performed in two-step operation. The analog signal is first passed into an anti-aliasing filter, where it band limits the incoming signal to cut off all the higher frequency signals, and then the band limited signal is passed into an analog to digital converter to convert it into a digital domain signal. And then this digital domain signal will be used for DSP processing. If we have to understand analog to digital converter, it is operated in two-step algorithm. One is the sample and hold circuitry, where the continuous signal will be converted first into a discrete time signal, and then a quantization process will convert the discrete time signal into a digital signal. With the details, we'll look into it very soon. Now, in order to perform the sampling process, a Nyquist criteria has to be compulsorily followed, wherein the sampling frequency should be selected such that it is twice the uh, maximum frequency of the incoming signal. So in order to band limit the signal to the maximum frequency f, only the sole purpose of this anti-aliasing filter is present. So we look into it by an example. We take a sinusoidal signal of 1 hertz. Let's say we need to perform this is an analog signal. We need to perform sampling on this signal. So we sample at a frequency or sampling rate of 10 hertz, for example. Then the discrete time signal will have a frequency which is given by the relation f by fs. So the frequency f of the analog signal divided by the sampling frequency itself. In this case, it is 110 cycles per sample. So that's the representation of this discrete time signal. So once it is converted into a discrete time signal, it should be observed that the amplitude level of this signal from +1 to -1 has infinite number of levels, and it is impossible to convey information from all the levels which is perceived from the signal. So it has to be mapped into a fixed number of levels. So it's called as quantization process. So all the levels are mapped into a closest level into the defined quantization level and converted into a digital form. So all the signals are from the analog signal are converted into a digital signal which represents a set of zeros and ones. This signals in the form of zeros and ones will be used in digital processor for further processing. So this is the complete process for sampling. Next, we move on to the second principle. Here, once the processing is done, so let's say the real world signals are no use if it stays in digital domain itself. So we have to convert it back to a analog signal in order to perceive information from it or get the various parameters from the same. So in order to do that, the digital to analog converter will be helpful for the conversion of digital domain signal and reconstruct the signal from the digital domain. So this reconstruction is mainly an approximation of the original signal. So let's say what we mean by approximation, it's that it is never actually the exact same signal what we was inputted at the ADC. The loss of accuracy or the reconstruction approximation being not matched to the original signal is only because of the quantization error or the digitization process itself. So if we want to look into one of the example of these loss of accuracy, then The same example I took before, the 1 hertz signal, if sampled instead of 10 hertz at a lower frequency of fs equals to 5 hertz, then we can observe that all these samples are related in such a manner that the negative amplitude of the original signal is being clipped off. So practically speaking, any interpolation, advanced interpolation methods, or if we use, the information between sample number 3 and sample number 4 is completely lost. So even if you recover the signal, it need not be exactly matching to the actual original signal. So original signal information is absolutely lost in here. So in order to overcome this phenomenon, we consider a concept called oversampling to reduce the errors from approximation while reconstruction process. So these are the two principles behind DSP. So we talked about or understood what DSP is, and we looked into principles like sampling and reconstruction. And I also told that the reconstruction process or the sampling itself has lots of errors, and it is never possible to recover the exact a signal that was available to us as an input. So even then, even though we know that there are errors due to quantization, we still prefer DSP. Why do we do that? Because of its advantages. Let's look into few of the advantages which compared to that of the analog signal processing. One is the complexity. The digital controllers are capable of performing complex computations at very high speed. For example, let's say we need to design a system with very complex operations. Then all we have to do is choose a processor. We write software code using our SDK, and then burn the software on the chipset. Then the design is ready. So it's that simple using a single processor, and any such complex operations could be performed. But in contrast to the analog signal processing, each time a new design is to be implemented, then a complete analog circuits has to be designed, recreated, or verified in that manner. And sometimes the cost of this analog signal would be very high than the digital signals, and it would end up very bulky and heavy. So in other words, digital processing is very compact and low cost. And other point is that the software programs could be are very flexible and easily modifiable. It could be made more robust for maintenance and more robust for verification process to achieve better design, processing, and final quality management for the final product. Then the second advantage is the accuracy and precision itself. Let's say I did tell that there is loss of accuracy during the processing signal chain, but it should be observed that let's say we achieved a certain amount of accuracy using the reconstruction process or the sampling process. Each time you run the code, or every time the experiment is repeated, the same amount of accuracy could be expected. The amount of precision is exactly repeatable. So in counterpart of analog processing, it is solely dependent on the circuit components, and it largely affected by the tolerance of each and every component. So it cannot be guaranteed to get the same amount of accuracies for every repeated experimentation. So digital processors, well, since it is all in software, the precision could be highly controlled. Then the next advantage is the storage, where once the digital or the real world signals are converted into a digital signals, it could be stored in a form of volatile or non-volatile memory. This memory could be used later on in any other processes, or in a process where it is needed, such that the signal processing is done in an offline environment and so on. So it is very reliable and flexible in this manner. So even the software designing team in industry, we actually collect loads of data, and then we perform some modeling on that data, and have a certain amount of verification even before moving on to the system design itself. So this is where storage is very important. And in counterpart, the storage of analog signals is nearly impossible. It's not like it is possible to store few characteristics of the signals, but it is nearly impossible to store and make robust storage as compared to digital signals. So we looked into advantages now. Let's take a grasp of disadvantages. We talked about analog and digital conversion and digital to analog conversion. This is a overhead for the signal processing chain, which means that a small amount of additional time is needed to perform these two operations before the processing itself begins. So it becomes a process overhead in that manner. And another disadvantage is the frequency limitations. It is not very practical to design an analog to digital converter for high speed applications or high speed signals. And it is preferred in that cases to convert the high frequency signals to lower baseband frequency conversion. That is the intermediate frequency. It's called mixing to intermediate frequency. So once this intermediate frequency is obtained from the high frequencies, only then we can perform digital processing for that signals. So when we look this additional process, it is again a overhead and it takes additional time in when compared to analog signal processing. So even then we have very minute disadvantages of digital signal processing. We do prefer and uh, we do, I mean, for the applications or future development, we do prefer DSP in that case. Look into few of the functionalities of DSP systems by seeing a simple demonstration. I would be considering a signal with multi-band or multi-frequency signal. Uh, I Today we'll be using a tool called GNU Octave, which is an alternative for MATLAB. It is used to script MATLAB code and then execute it, and it is a license-free software. It could be used as an alternative to MATLAB. Uh, as talking about multiband frequencies, I have considered three frequencies here. Multiband frequencies is that signal which has more than one channel embedded into it. So I have considered, for example, a channel with frequency 15, channel with frequency 45, and channel with frequency 80. And my signal is a sinusoidal signal for just a example. And my multiband frequency is a compound signal consisting of all three channels. We'll look into how the signal actually looks. When you look into a time domain plot of that signal, it is really not understood. It is a periodic signal, but what frequency component does it have? What is the periodicity of the signals? Understanding all these is really difficult. So let's do it in further analysis. So for first, this is an analog signal for now. In simulation process in MATLAB, generating an analog signal is very, let's say, not practical. So I have generated a signal with very high sampling frequency. Initially, I've considered a sampling frequency of 1000 for maximum frequency component of 80. In this case, I have smoothened out all the frequency or let's say the adjacent samples, and so the signal looks very smooth. So in order to perform sampling in our example, I would be down converting the given signal from the high frequency component to my required frequency sampling frequency. So for that, I will band limit and assume a maximum frequency for my signal. So since I already know the amount frequency range of my signal, so which is 80, I will assume that maximum frequency and band limited to 100 hertz. So such that my frequency sample or sampling frequency is considered twice the maximum frequency, that is 200 hertz. So using this, my downsampling process will accordingly downsample from a higher frequency, that is 1000 samples, to a lower frequency at 200 hertz. Then this process of rounding and multiplying it by 256 is my quantization process, which maps all the floating point amplitude values into a fixed uh, number of amplitude levels. So this is one of the quantization methods. And then we look how the amplitude or the sampling process has been achieved. So the analog signal, what we consider here, is sampled at a discrete time or fixed time interval, and it will be uh, very close to the analog signal, but it cannot be perceived at what frequency does the input signal is really having. So we need to make a frequency analysis. Since in here the simulation we already know the three different frequency component, but in real time applications we won't be, let's say we're not aware of all the frequency channels of the multiband signals. The first process, we need to convert the time domain signal into a spectrum domain analysis and see what all components does this signal really have, and then make some decision for signal processing. So first step is spectrum analysis. So I'll be using an FFT operation on my digital signal, that is the sample signal at 200 hertz, and use only the real-time spectral frequencies. That is, the FFT output will give me both imaginary spectrum domain and the real spectrum domain. For analysis purpose, I will be only considering the real frequency spectrum. So let's if we have a real frequency spectrum from 0 to 120 hertz, then I have three different peaks in my plot. So if I zoom in, yeah, if we carefully analyze that these peaks are appearing at a precise frequency value of 15, 45, and 80. So we have verified that the sampled frequency has preserved the frequency components of the original signal, which was at higher frequency, let's say analog frequency in my case. Later, based on the applications, let's say I need to extract these particular frequency component and perform useful or desired operation only on that particular frequency component. In such a cases, we use filtering process to extract a certain amount of or certain band of frequencies, um, and it's called as filtering process. So in my example, I'll be taking an ideal band pass filter to filter out only a certain amount of spectrum from the desired signal. So I'll show you how my ideal filter is exactly looks like. So for my example, this is an ideal filter with a lower cutoff frequency of 40 hertz and higher cutoff frequency of 50 hertz for my frequency extraction of 45 hertz signal. I'm using an ideal filter here because just for an example and showing a demonstration, and it is not very practical in going and implementing this particular example in a real world application, because let's say it needs more number of samples to approximate or get a very good results, and there are well and optimized way of designing filters. So yeah, for that details probably you need to look it up later. So here the ideal filter, I have specified the lower and the upper cutoff frequencies. uh, and now the transfer function, we have looked into the transfer function of the bandpass filter and multiplying it with the frequency domain signal of our sampled signal. Then this is nothing but performing a convolution operation in time domain. So this process will extract me the IFFT, or the inverse transform of this frequency component will extract me the uh, particular frequency that I'm interested in. So my frequency 3 I have plotted is the extraction of this particular frequency at channel 2. So if we look at the time domain analysis of that signal, so this the blue plot shows the original signal that I had generated, and then the red signal is the reconstructed signal which preserves the frequency of my information. And the frequency domain analysis says it is still having a 45 degree value. So now we can verify this with extracting some other channel like channel 1, since I have 3 channels with me. And let's see if it still works. Yeah, so my lower cutoff frequency is at 10 hertz and upper cutoff frequency is at 20 hertz for my band pass transfer function. And then my extracted signal is still preserved. And if you see the reconstructed signal most likely matches with the original signal. Similarly, going with the third channel. Yeah, the third channel at 80 hertz has given me a good approximation of the frequency component of the original signal. If you observe the red plot, it is not matching to the original signal, but the frequency is preserved. So if you look at the frequency component at 80, it is only because I have considered a band limit of 100, while my frequency what is interested is at 80. So if I had considered a much higher frequency sampling frequency, then recovery could have been very good, uh, or use a better interpolation process, whatever it is. So we have looked into two of the DSP functionalities. One is the frequency transformation and one is the convolution process in frequency domain by considering the bandpass filter transfer function and the frequency converted of signal of the incoming message. Next, we'll look into one of the scenarios. What really happens if we take a sampling frequency lower than that of the maximum frequency whatever we have. Let's say, for example, I choose a frequency of 110 hertz. My frequency band limit is 100 hertz, which is obviously less than the maximum frequency component. If I sample at 200 hertz, obviously according to the Nyquist criteria, it should be fishy with respect to the outputs. Let's see what exactly happens. My figure 3 says I have no signal. Let's see why that is the case. Yeah. If I look into the frequency domain analysis of my sampled signal, I have 3 peaks still. My frequency channels are 15, 45, and 110. If I look into my peaks, I have 15 hertz, 45 hertz, and 90 hertz. What is really happening here? But at 110, my signal is absent. So this 90 hertz is an alias of this 110 hertz. So this concept of aliasing, it's nothing but when sampling is performed on a non-band limited signal, the higher frequency components, which is less than the half of sampling frequency, will appear as alias signal. So here the 110 signal has appeared as 90 hertz. So this is an alias. So with this example, we have proved the sampling theorem, and we have understood well with two of the functionalities of DSP. From our demo, we looked into various fundamental concepts, or let's say two specifically. One is the frequency domain transformation, and then the other convolution process. So this I have implemented on MATLAB, not the DSP processor. We'll look what exactly is a DSP processor. So likewise, there are many other functional fundamental concepts like correlation, or it could be digital filtering, what I showed you with bandpass filter, and then the decimation and interpolation for multi-rate signal processing, or even the differentiation and integration process. Differentiation is used for determining the maxima and minima of the signal. Integration is to determine accumulated signal parameters over a given time period. So there are so many of these functional individual functionalities which could be implemented on a DSP processor, or in combination of this to provide or design a compound system, or a signal processing application. So coming to the application perspective of DSP, it is majorly used in telecommunication, uh, right from the beginning of second generation. First generation is completely analog processing. The second generation, 2G, 3G, 5G, and the future 6G, all will will be followed DSP processing signal chain. And then coming to the satellite navigation, either take it GPS or GLONASS, or even the IRNSS or NAVIC system that was recently launched and been successful by ISRO. Any of these follows radio signal, radio reception in digital domain, and the speech processing, like in video conversation or audio conversation, and image processing in video conversation, and even in the medical applications like MRI and X-ray imagery, where the internal organ analysis is done in a more detail using artificial intelligence for further advancements. And other domain is instrumentation. For example, let's say the multimeter or DSO, digital oscillators, all are following a DSP signal chain for making it more compact and robust measurement systems. So the processing demands has led to the evolution of various platforms for DSP system implementation. One is the DSP processor. There are many example or chipsets that are available from Texas Instruments or analog devices. All these processors are could be designed with simple programming languages like C, C++, and sometimes assembly for optimistic code generation for certain functionalities of DSP processor itself. So this is all software development system using a DSP processor. There is other platform with completely digital circuits, that is the field programmable gate array, that is FPGA. Certain FPGA chipsets are Xilinx and Intel. These FPGAs are software programs written in a hardware descriptive language. So all the DSP scripts or the DSP digital circuitry are designed on software and being used in FPGA domain. And then another platform is modeling and simulation, what we exactly looked into my demonstration a few minutes ago. The simulated signal, what I considered is completely generated on MATLAB scripts, and the modeling of the DSP system is performed using a simple operations. So either MATLAB or Octave could be used for this purpose, and even Python could be very considerable competent in case of modeling and simulation for advanced data processing. There is, let's say, this modeling and simulation helps to analyze, verify the design even before it has been implemented into a embedded processor or FPGA. And then once the proof of concept is done from the modeling, we can later implement and get successful results after implementing the design on embedded systems. There is one other domain I would like to take as the automobile field. The ECU, the electronic computing unit, which is also a DSP system, which actually assists, which actually is used for driver assistance or autonomous driving for cars, for example. These uses DSP processing too, and it is specially designed to operate a large amount of data processing in very low power and very specified DSP operations. Uh, yeah, and similarly, many platforms could be given with power industry like PLC and machineries, etc. Yeah, and finally, we will see what the job opportunities and the career path one should choose in order to streamline themselves with DSP engineering. There are many fields, if one is interested, is communication field, where the software defined radio engineer or the RF engineer are very highly demanded jobs right now, because a few of the companies like Qualcomm, Samsung, Ericsson are currently working on 5G evolution and bringing up future 6G, and continuously evolving the current radio technology for mobile and telecommunications. And even other domain like GNSS engineer, like optimizing the performance of satellite navigation systems from GPS, GLONASS, IRNSS, BDO, etc. What so many examples in there. And then coming to this streamline of image processing, one could consider entering into a computer vision engineer or biomedical image processing, where the medical domain requires large number of image processing with artificial intelligence in that domain. And then there are other domains like audio industry, power industry, or automotive industry. In audio industry, all these industries, they are requiring engineers or persons with a title algorithm engineer. So let's say I give one example, like in power industry, the battery optimization for battery consumption and charging optimization algorithms, all these are performed on DSP platform. And then audio, obviously, continuous evaluation of the speech processing, and uh, automobiles in terms of ECU and autonomous driving and driver assistance systems. And the next domain which would be interesting is machine learning engineer. The concepts of DSP and neural networks will be combined here to form artificial intelligence systems or machine learning algorithms. I could give you one example here is the prosthetic arms and legs. Uh, let's say a system which interprets the brain waves and performs movement of the artificial arms or legs. In this system, the brain waves, the person has to just think about moving his arms, then the limbs would be operated accordingly. So this system has been continuous under evaluation and further evolution into prosthetics. So overall, coming to the final slide here, we looked into certain DSP principles, having to looking at the analog to digital conversion and digital to analog conversion processes, where it's the backbone of DSP engineering. And then we looked into certain functionalities of DSP and the processing demands, and how the evolution of this demand has been fulfilled using various platforms like DSP processor or FPGA, or even the modeling platform like MATLAB or Octave. It's completely been evolved in that sense. And we looked into certain applications and what all streamline one could consider in order to pursue this domain of DSP engineering.